I shall continue from where Zoltán stopped. And looking at monitoring techniques, not NDT techniques, to identify the effect of traffic on the structure itself. So most of the testing and monitoring techniques are looking at the large as it is without any loading. But I'm also interested in knowing how is the large responding to the traffic, so live traffic. One of the methods that was mentioned is acoustic emission monitoring. So that is effectively using a small microphone, which I believe is useful for medical purposes. So if you put it on an elbow or a knee, and you hear noise, cracking noise, crunching noise, as you're moving your elbow, then you know something is wrong with you. So the same principle applies to masonry bridges. You put the microphone. Oh. Shall I start again?
No.
Okay, right. So basically the same principle applies, putting the microphone on the structure, on the bridge, and listening to cracks. First of all, we tried testing the system in the lab at University West of England in Bristol, or before that at Salford University, and then went out and tested some bridges in situ. So these are some examples of the process of fatigue deterioration. So this is a typical prism which represents a small section of the arch ring. So imagine you're taking 5 bricks out of the bridge, out of the arch, turning it vertical, and replacing the traffic loading as compressive loading. So we do this cyclic loading at least 3 million times, or as soon as it breaks, until it breaks. These are 2 tests. The first one is under static loading. So you increase the loading until the prism fails, and looking at the noise. The level of noise is measured in amplitude and is pictured against load. So as you go to the right, the load is increasing. The amplitude, the noise level, is increasing, as you see, by the red dots getting higher and higher. There's a base noise below about 40 decibel, which is just background noise, so we are not interested in that. So what is interesting here, that above 40%, the noise level is starting to increase. So that's 40% of the strength of the brick, of the masonry. And below 95%, it shoots up. Amplitude is on a log scale, so the vertical axis gets much more serious at every small step. So there is a change in behavior after 40% and after 90%. So if you think about elastic and plastic region in stress strain diagrams, which you're probably familiar with, so up to 40% is about the elastic limit, and over 40% is the plastic limit. So over 40%, you've got some minor micro cracks developing in the structure, which then develop into macro cracks just over 90% or 95%. The second graph is doing something slightly different. We're keeping the prisms and applying long-term cyclic loading, looking at the noise level and how soon that is going to break. Initially, the noise level is relatively high, then it reduces, and about, you can't see it very clearly, but about 90 or 95%, then 90%, it goes up again. This is kind of a bathtub, so it starts off high, then decreases and goes up again. So this is how quickly failure occurs in the masonry. Now I'm only talking about masonry rather than bridges at this stage. This is an example of an arch without soil above it. So this test was done by putting a certain load on, cycling it for 1 million cycles, and then increasing the load to 16 kilonewton, 18, 20, up to 34. The numbers don't really matter. what is interesting, I find that the noise level here is expressed as amplitude, absolute energy per cycles from the acoustic emission monitoring. Suddenly, the noise level goes up. So you don't know something is happening until it suddenly happens. Going out and testing acoustic emission on site. This is a road masonry arch bridge with lots of cracks, all the variations that you can think of, installed permanent monitoring on that. So the acoustic emission sensor is very small, like that, and was very quick to install. So it took probably two or 3 hours to get the whole system installed. We put 8 sensors on the bridge, various locations. And what we are looking at here is the red dots. If you can see, I'm not sure you can see it from the back, but in for some sensors, the noise is higher. There are some high spots. In other ones, there isn't very much. So picking out the high amplitude locations, some of the areas are struggling, some of them less. So you can identify where the issues are, and then initially, and then you can focus on your sensors on the region that's causing you problems. We tested the bridge before and after refurbishment, where so the yellow bars are showing before refurbishment and the blue ones after. You can clearly see the change in noise level, so this indicates that there has been some benefit to the works. Another example, the system was put on a railway bridge just under the railway line by 6 or 8 gauges. These are 6 of them shown, 1 to 6, and sorry. This is under light traffic, light passenger train. You can't see anything really very much. The second one is slightly different. You can see a lot of red dots. So that red dot is not good, especially if it is over 40 decibel. So about that. So 3 of the sensors are very active and 3 are not feeling very much. And the 3 which are noisy are, is it? Oh, pointer. If you can see that the 3 just below the track. Obviously, the trains are hitting that most closely and creating more probably deterioration indoors. Below a certain depths, about 1.3 meters, the noise suddenly reduces, which actually coincides with the backing. So you can guess that from looking at the bridge, as Bill has been mentioning, or you can listen to it and you get similar, you just confirm what you were probably expecting. And what was also interesting, that the hits actually coincided with the number of tracks, so to each axle bogie. So a quick summary for acoustic emission, you can identify damaged areas, you can listen to the response of the structure to the live traffic, whether it's light traffic or heavy traffic. You can listen to the changes over time. And you don't need to close the bridge. You can do it under normal traffic. And that, just for information, for later, just in case you're interested, some indicative costs. Other ways to listen and listen to the response or look at the response of the structure to live traffic was mentioned before, as the Morey telltales. Some other techniques is digital image correlation, which is taking pictures in like Morey, similar to exactly the same principle. Morey, photogrammetry, take one image without loading, one image with loading, and see where the particles move to or shift to on the digital photograph. There's one company I know of that does video recording using digital image correlation rather than stills. So this can be helpful by looking at the response at certain locations to traffic. As an example, a bridge was filmed or videoed from about 50 meters distance. 3 cameras were put up, each of them looking at one detail on the steel arch at the bolt. And this is what you get. You get a picture with the strain distribution. So it could be helpful, just in case you need it, to look at any particular detail. And they also identify the loading and deflection. You can use this picture, this output, as digital strain gauges afterwards. So you can, instead of installing them physically, you can have as many unlimited number of strain gauges. This was an application on one of the railway bridges, Masonry arch as well, as the train was on the bridge, just going on the bridge, and train just leaving the bridge. And we looked at the color scheme, which it was only a trial, so you could improve this quite dramatically and get much more out of it. We could very easily, from this simple film video, we could get the deflection out at certain locations quite easily. So digital image correlation typically gives you a response of up to about 0.5, 0.01 millimeter resolution. You can use it from about 50 meters, so that can be helpful. And you can use any number of strain gauges afterwards. Another method to listen to the bridge or the structure and how it responds to traffic loading is accelerometer monitoring. We are using one which is called, which is a sensor, an acoustic accelerometer sensor by a company Sensor, and this is called CX1. So this particular accelerometer is we have been using because of its sensitivity. It was developed for structural purposes, for monitoring walls after earthquakes, if they're still moving or if they are stable and safe to enter the building. The principle is to put the accelerometer on the bridge for 8 minutes without any loading and rely on the background vibration. So the background vibration gives us a very clear picture of the structural response to structural frequency response. So it is like a footprint. Unless something changes in the bridge, the frequency spectrum won't change. So it would tell us the key frequencies up to 1,000 hertz. We are recording 2,000 times a second, so that gives us enough data for statistical analysis and fast Fourier transforms to get that. And this is an example of the output. On the vertical axis, we have acceleration, so how big the movement, and the horizontal axis, we've got the frequency. So in this one, we've got the frequency up to 62.5 hertz, but we go up to 1,000. So 62 hertz is normally relevant to most bridges without any traffic loading. So that gives you the key frequencies. Most people analyzing and doing finite element modeling, looking at acceleration and frequency, look at the first 4 or 5 modes and the shape of the modes. What we are interested in is not what shape they are, but where they are and how and if they change. This is one bridge with X, Y, Z coordinates recorded with the CX1 accelerometer, and 2 sets of pictures, one damaged, one undamaged arch. And although if you're looking far, you won't see it, we are looking at the shifts in frequency. So we can see one of the same, I don't know, about 5 or 10 hertz shifting as on the damaged span, so comparing spans. This is an example of the system being used, just put on the bridge. There was a railway bridge, but the problem is that there's usually traffic. And this is another one for the system when we're using with solar panels because there is no main spar on the bridge. And this is a system being installed in one of the bridges. So it's a very small system, very easy to install or use it permanently or for temporary applications. These are two recordings, X, Y, Z direction. So X is transverse direction, Y is longitudinal, and Z is vertical. So we are looking at the frequency footprint in all three directions. The first three are for the signature of the bridge without any traffic, and the second one is with traffic on. You can probably only see the shape, which might be different. What you can't see is the scale. The second one is about 4 times bigger. So you've got a very small background vibration, which very clearly indicates the key frequencies. However, if you've got traffic loading, it overrides everything. Now, how can you use the system if you've got a live bridge with traffic almost all the time, day and night? This is one of the bridges where the system was installed permanently. On the vertical axis, we've got the frequency up to 120 hertz. On the horizontal axis, we've got 24 hours. The yellow line is the temperature, which doesn't make a huge amount of difference in that case. We start during the night. This is during the day, midday, and this is midnight again. Can you see differences in the density of the blue dots? So during the night, you've got more dots lower down about 2 or 5 hertz. During the day, you've got more dots or more frequencies around 90 or 100 hertz. Therefore, during the day, you've got more traffic loading, so the high-level dots frequencies relate to traffic noise, and the low level is to the natural frequency of the bridge without any loading. So this is good news. So that means by using the system, you can monitor any changes or hopefully pick up any change during day and night. And the only reason we can do it that we analyze the signals every 8 seconds. If you did it for an hour, you only get 1 dot, which would be the natural frequency with and without traffic would be mixed. But there are certainly 8-second intervals where there isn't very much traffic, so you can pick up the traffic noise and the dead noise as well. So the ideal period for monitoring is 8 minutes, but you can do it for 1 minute. It's also sufficient. What if anything happens in the bridge? There is corrosion, crack, the signature will change. So what we are looking at is change in the signature. It depends what sort of change it is. We will be able to relate that to the structural element and then tell the bridge owner there is a change, go and have a look, and it's likely to be something. And that's from me for now. Thank you very much.